Hi, good day, everyone. Welcome to week five. Okay, week five will be primarily looking at covariance correlation by varied distributions. That means two random variables. What is their joint distribution, joint probability, and the conditional probability for involving two random variables? And what is their distributions and some of the common distributions. So this is the main side. Okay. So first, let's look at some of the slide highlights. So week 5.1, covariance and correlation. So by means two, okay, two random variables. And use students' height and weight, what is the different combinations to uniquely characterize one of the student. Relationship between random variables. Okay, so if there's two random variables tend to move in the same direction, then we say they have a positive correlation. Let's say a student's weight and height. We have observed in human population or in typical populations of human being in different countries, different communities. We're seeing that with the increment of the weight, the height generally increase. So these two random variable has moved in the same direction, so they are positive correlation. Okay. So covariance of X and Y, how do we measure? How do we measure the relationship, whether they're moving in the same direction or different directions? We can use it called covariance measure, okay? Covariance is using this formula, expected value of X random variable 1 minus the average value, mean value of the random variable X times the second random variable y minus the mu y and time them together. Since this is the expectation, then we need to time the joint probability of x and y happen at the same time. So x minus mu measures the deviation of random variable, individual random variables, values, measurement deviate from its mean. That y the same, okay. Okay, so positive correlation. So if the covariance value can take from minus infinite, very large number, to 0 to positive infinite, theoretically. So if it's a positive value, then that means x and y tends to move together in the same direction. Okay. Okay, then a negative correlation, then one is, so the covariance value will be a negative value. So they are moving in the two different directions. So X is hours of exercise. With the increment of hours you exercise every week, in general, the body fat will reduce. So yeah, so they are moving in the opposite direction. So they are going to have a negative correlation and a negative covariance value. So no correlation. So it's 0 means no linear correlation. Covariance X and Y. Okay, covariance. So these are primarily covered in the video lecture. So okay, so covariance is a measure that can range in the real number. So we have defined another coefficient called correlation coefficient. It's actually linear correlation coefficient. Low xy is defined as covariance of xy divided by the sigma x and sigma y, standard deviation of x and standard deviation of y. So the pxy, the low xy will be in the range of -1 to +1. So it's normalized value. It's always bounded in this range, -1 to +1. Okay, so here is a few figures showing two random variables on x-axis and y-axis. What the value of x it can take and the value of y it take. Then there's 1,000 dots, 1,000 measurements or data points in this graph. Okay, so for the first graph, it shows if you calculate, the low is near 0, so there is no linear correlation. then it's a slightly positive correlation. Then we move to, say, low xy plus 0.7. You are seeing if the data is distributed in this manner. We are overall seeing that with the increment of x, the y also increase. Then for this chart, when the x increase, then the y actually decrease. So there is a negative relationship. So it's minus. So it's a negative. Okay, for this 5.1, recall the two properties that we have learned in the past few weeks. So regarding the variance, so variance ax plus c, so there's only one variable x, okay? Then it is equivalent to the a square variance x. So recall that one. So this is a univariate, only one variable x. Then for two variable x1 and x2, if we plus them together, we want to calculate the variance with assumption of x1 and x2 are independent. Then variance x plus y is equivalent to variance x1 plus variance x2. So this is established when x1 and x2 are independent. So now we're extending to the following more general properties. So variance x1 plus x2, when we do not know whether x1 and x2 are independent or not, then it will be equivalent to variance x1 plus variance x2. Let's set the a, b, c all equal to 1 or c equal to 0. So a, 1, b, 1, and c, 0. So we're going to see variance x1 plus variance x2 plus 2 times covariance x and y. Okay, so that will be this formula. Okay, that's this formula. So also recall that the covariance x1 and x2 is equivalent to low xy linear correlation coefficient times the sigma x and sigma y. Okay, so you are seeing this second formula. See, this portion is the 2AB covariance x1, x2 is equivalent to 2AB low x1, x2 times x1, low sigma x1 times sigma x2. Okay. Okay, so this is the overall formula. Let's say if the b is minus 1, yeah, it's minus b, then you use minus b squared, you will get still a positive b, then 2ab becomes minus 2ab. So these are some of the formula that concern about the two random variables, their variance, and their relationship. Okay, we'll look at 5.1. Okay, so let's look at 5.2. 5.2 is bivariate distributions. Okay, yeah, bivariate distribution. Okay, independence of random variable. Probability of x1 and x2 happen at the same time, taking a very specific value of small x1 and small x2 is equivalent to probability of x1 times x2 if they are independent. If they are independent. Now, if they are not independent, then we're looking at something else. Okay, so a company produced a hot dog bun, took 10 of them to inspect quality, then each consists of a bun and a hot dog. So hot dog, later I will call it a sausage. Okay, bun and a sausage. So the bun not meeting the quality standard follow a binomial distribution with 0.1 probability. And the sausage is, the defect rate is 0.2. So sausage is more likely to have defect. Bun is less likely to have defect. Okay, so bivariant binomial distribution is either defect, not defect, right? Recall that. So next is what is the probability of two random variables? So they are joint random, and with the assumption of the two random variables are independent. So the number of defects you can detect from the bun is independent to the number of defects you can find from any sausage. You can think these two production in the factory, the two production line are totally separated. They are not related. Or you can even think there's two different factories, two different sellers. One is specialized in manufacturing buns located in Jurong East. Another factory is specialized in producing sausage, and it is in East Coast, allocated in East Coast. So these two are totally independent, okay? So no influence to each other. So now let's have a look. Okay, so I'm going to run a few visualizations to help you to better understanding the relationship of these two. Okay, so I'm going to open the R. I'm going to open the R, but I need to find the R script. So the R script you can find in the seminar group. You pick up your seminar group class group. You go to the seminar specific content. So week 5. You are seeing a few of the document here, a few of the script here. So the second one is the demo. So demo is used to complement the slides, while the R tutorial solutions is for the tutorial. So you download both of them. So download both of them. So download both of them. Yeah, and you also see that the complementary rules for identifying population and the sample. So this is for supplementary reading for you. So you read this document to overall understand in this course or in the test, um, when should you treat the data that you have as a population or the sample. So there is a comprehensive rules. So for example, you can differentiate population and sample based on the given symbols and notations on the provided data set. So population and sample, they have different notations. So let's have a quick look. So here what they are seeing on the left side, on this left side, you have population P, sample on the right side is S. Okay, so the size of the population is uppercase N, N, big N. Then sample size is S. Recall a few weeks ago, I think in week 1, we say the size of the sample space, N, which is the length of the number of outcomes in the sample space. So you can use R code length parenthesis to get how many elements are there in the list or in the sample space. Then for population, mean is mu. Then for sample mean is X bar. Okay. For population, standard deviation is sigma. Sample standard deviation is S. Population variance is sigma squared. Then S squared is the sample variance. Then for the covariance is XY. Okay, COV In sample covariance, sometimes it's written as SXY. Okay. So in R, there is a function called covariance function. So the covariance function will calculate the sample covariance, sample covariance. Then low XY is the population's linear correlation coefficient. Then RXY is the one for sample. Okay, so that's the notation. How do there are more comprehensive rules to determine whether this is a sample or population. Okay, so please read it. Please read this. Okay, so now next is we are looking at this one, the week 5 R demo. Okay, I've already downloaded here R demo, this one. So after you open it, let's double click to open it. It will be open in the R software. So it's open in the R software. Okay, so let me clear my R working space. Let's go to the very beginning. Okay, covariance and correlation. I think let's get a review of it. So you are not required to really understand the code at the script level. So this is just for visualization purpose. Okay, so for visualization purpose, this is for visualization purpose. Okay, so this is showing you that we're simulating a few scenarios. Then what is the calculated correlation coefficient? Then next is showing you that if you have a relationship like y equal to x squared, so it is drawn here, then you you use a formula to calculate the low xy linear correlation coefficient, you will find that the linear correlation coefficient between variable x and y is near zero. It's near zero because this is simulation. Theoretically, it will be zero. But there is a clear relationship between x and y. So although it is not a linear relationship, so the low xy is a good measure if x and y has somehow a linear relationship. But if it has a relationship but it's non-linear, then low xy might not be able to capture the non-linear relationship, the strengths of non-linear relationship. Okay, so you can actually calculate the covariance of xy is near zero, 0.002353. So the relationship between the y and x is actually near zero. But it's clearly there's a nonlinear relationship. Okay, so now we move to 5.2, the bounds situation. The bounds situation. Scroll down exercise. So these are the exercise. Step 2. Okay, need to find the bound. The bound it should be around here. Bivariate. Okay, visualize a hot dog example. Okay, hot dog, bed buns. This is a bed bun. Set up the plotting windows to display 2. So we're first showing the defect buns. Okay, so we're seeing the defect buns. Binomial PMF is probability mass function. PMF, probability mass function. So 0, 1, 2, 3, 4. These are x-axis, other defects. So then you have the defect sausage binomial distribution. Okay, so these are the PMF for buns and sausage. Okay, so next we assume the statistical dependence between the buns and sausage. Then we can calculate one bad buns at the same time as two bad sausage. What is the probability? Now it's shown here. This is the probability. The probability is 0.116991. So one bad buns, two bad sausage. One bad bun, two sausage. Okay, is 0.116991. Okay, so we align with the slide. So next is we're going to show you visualize a joint probability distribution, the probability of bad buns and bad sausage taking different number of defects. So you're not required to understand the code here, but understanding what we want to visualize. For the two distribution, number of trials is 10. Okay, probability of defect for buns is 0.1. Probability of sausage defect is 0.2. These align with the slides. Calculate the PMF. So create a grid of. Okay, so next we are going to do is 3D plot. Okay, so this is a joint distribution of defect buns and the defect sausage. Y is the defect sausage. X is a number of defect buns from 0 to 10. Then a number of defect sausages is also 0 to 10, right? So 0 to 10. And you are seeing that here is no defect when number of buns defect 0. Defect of sausage also 0. The probability is 0.03, about 3.7%. Okay, so then 0 defect of buns and 1 sausage defect, then 0.09, about 10%. Then which one is highest? The highest is 0.116997. So this is 1 defect in bun and 2 defect in sausage. Okay, so when you have access to this R script, you can also generate this 3D joint probability distribution of these two random variables, and you can observe and interact with them. Okay, How many dots are there? Do you know how many dots are there? How many dots are there? So there will be 0 to 10 and 0 to 10. So there will be 11. 11 times 11, it should be 1 to 1. So it should be 1 to 1 different dots. Each of the dots are associated with a probability, right? So they're associated with a probability. So that's a joint probability of these two variables. I'll call bivariate probability distribution. So now all these probability, if you sum them together, 1 to 1 different probability, and then sum them together, they should be equal to 1, 100%. Okay, good, good. So this is the one that I want to demonstrate to you. So this is actually this joint probability. Observing two random variables taking certain values at the same time. So one defect in the bad bun and the comma actually means and one bad sausage, two bad sausage. Okay, so comma in general means and relation or intersect. So this is shown here. Okay, so I add a little bit. Px and intersect y is equivalent to px comma y. In general, a comma equivalent to px and y. Okay, so this is the way that you interpret x comma y, means x and y taking a certain value and they happen at the same time. Okay, and there will be a few other formulas. Okay, so px given y, so conditional probability is equal to px and y, or px comma y divided by py. Okay. Okay, so we have covered this sausage bun, then loading CSV for examine the number of cars. So this is, you follow the video lecture, calculate the marginal probabilities and what are the logical operators. Okay, so next we're moving on to this 5.3 conditional expected value. So recall we still have the conditional probability, the probability of an object being read when we know the object is a ball. Given the ball, okay, we know it's a ball. Recall we have our rule of thumb is when you see the condition it's a ball, so you remove all the triangle and retain only the ball. So 1, 2, 3, 4, 5, 6, 7, 8. We have eight balls. 1, 2, 3, 4, 6, 7, 8. Yes, we have 8 balls. So out of these 8 balls, how many are red? How many are blue? Right. So red and the balls, how many? 1, 2. 1, 2. 2 divided by 8. We will have 1 over 4. 1 over 4. 1 over 4. 1 over 4. Then this formula tells you, okay, we can calculate using formula. So the probability of red object and that object is a ball over the total population. So this is the probability of red and ball. So red and ball is 2 divided by how many? 8 balls plus 4 triangles, there's 12. So we have annotate. Okay, so this part is red and ball is 2 red ball divided by total 12. Okay, so this is that part. Then probability of ball, 8 balls over 12 objects. 8 balls over 12 objects. So in the end, the joint probability is 2 over 8. 2 over 8. Yeah, it's 2 over 8. This is the same as what we directly calculate by removing all the triangles, retain all the balls. 1, 2, 3, 4, 5, 6, 7, 8. 8 balls. Then out of these 8 balls, how many are red? 2 are red. So 2 out over 8. Okay. So let's move on. So conditional probability. Then yeah. Okay, so okay, conditional distribution. So y taking a certain value, then what is the chance for x to be equal to different values? So here is a table. Okay, so I have 2 variables. Insurance company calculate the bivariate distribution of the customer car brand and blah, 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 blah. So So next is we want to find for brand 2, car owner. Brand 2 car owner, the probability of his car to be stolen is given by this. Okay. So it being given by this, we're saying y equal to 2. So y equal to 2 is only these two numbers. Then brand 1, brand 3, 4, 5. Rule of thumb is just ignore them. Only focus on y equal to 2. Y equal to 2, you only have two numbers. Then plus this one, three numbers. Then the probability x equal to 1 when given y equal to 2 is x equal to 1, then 0.01 over the entire sliced pie, 0.308. Then that's the conditional probability for x equal to 1 when brand is 2. Okay, then okay, yeah, and these two conditional probability will add it up into 1. And calculate conditional expected value. Okay. So here is the example. Suppose the insurance company charges the brand 2 car owner $200 premium under the condition that the company will pay $5,000 if the car is stolen. Okay, so I'm going to calculate the probability of being stolen. What is the expected compensation the company needs to pay, and the probability of the car is not stolen, then what is the compensation to pay? Okay, so $200 minus your expected value of the cost. So the cost to pay, okay, for brand 2. So the cost to pay is if it's stolen, or how much do insurance company need to pay? If it's stolen, is 5,000 times the probability of stolen, x equal to 1, y equal to 2, and this x equal to 1, y equal to 2, 0.032. Then plus, if the car is not stolen, how much do I need to pay to the customer? When the car is not stolen, this is theft insurance, so no cost, no money to be paid to the customer. So it's 0 times the probability or whatever. So you are seeing that $200 is I collect from the customer minus the cost, the potential, the chance that the car is really stolen and I need to compensate is about 40. Okay, it's about 40. Is 40. Yeah, if you want to get $37.66, you actually need to append a few of the additional decimal places. Okay, so there is a slight amendment to the video lecture. Okay, if it's a continuous random variable, instead of using the weighted sum, we're using an integral. I'm going to use an integral. Okay, so that's the highlight of this content. Then we're moving to the tutorial. Okay, so the main part of the tutorial, week 5. So I have a few questions. Then download the data file from the course site. You can use the following command to read this CSV file that contains discrete bivariate distribution of x on y and calculate the answer for the question below. You must know how to calculate variance. Now we're going to do this. Then we also need to week 5 question 2.csv. So these files, by now you should know where to get it. If not, either you can find it in the main course site or the seminar course site. So in the main, if it's in the main, it's generally in this place in tutorial questions and slides. So there is a consolidated data set.zip. You can download the entire thing, or you may find it in the seminar group. So once you have it, you unzip it. Okay, so once you unzip, you have this AB1202 CSV data set. Inside it, there is a data set using tutorial and video lectures. There are quite some data set used in the video lectures. We have consolidated for you and some of the data set used in tutorial. So for week 5, we happen to have to use 2 CSV files. So let's open and have a look. One of them, week 5, question 1.csv. Okay, you have X variable, Y variable, and the probability. So 3 columns. So X, how many rows? You have 20 rows. Okay, so probability is count 20, sum 1. Okay, so the probability sum together, it should be 1. I expect it to be summed into 1. Okay, sum to 1. So now let's read this file into your tutorial R script. So actually I'm opening this R solution 5.r. So this is my reference solution for you. Okay, so let's move to the top. Let me clear everything in my working directory and also clear all the plots. I clear all the plots, clear all the plots. Okay, so tutorial 5, question 1. You must learn some R, okay? So read the CSV file.choose header is the one that you are going to use. So read. So when you type read, it auto completes. You can move your cursor up and down the tab. Read. Then after that, say file.choose. Then you equal to false. Then header. The data have a header equals to true. LUE or true. Okay. So run this. Run this, you locate where your data set is. It is in CSV dataset, the week 5, question 1.csv. Open it. Oh, you are going to see it here. You just see it here. It will just read this file and display in the console, and you have nowhere to find it. So you need to assign it to a variable. So okay, Q1, you assign to a variable. You can use this arrow key to assign, or you can use a equals. I show you a few ways to do this. So once you run it, yeah, again, it asks you to select this file. Okay, so it says Q1 has been read to 20 observations of 3 variables, X, Y, probability, integer number. Okay, so let's click it. Once you click it once, the name, then there's a new window to be opened. So X value, Y value, and probability. So that means X random variable takes value 0, and the Y random variable takes 0. Then what is it? Uh, joint probability. It's 0.088%. Then you have 20, you add the probability together, you have 1. Okay. So next is asking determine each of the following probabilities. So x equal to 2. X equal to 2. What is the marginal probability? We don't think about anything about y. We just want x equal to 2. What is the probability? So we need to find out x equal to 2. The probability x equal to 2. X equal to 2. So we have this Q1 here. So we type Q1. If you run Q1, you just run Q1. It will display all the Q1, everything there. But now you add a square bracket. I just share with you a few better ways to display all the rows with all some of the rows with all the columns. So we add a condition there. So Q1 dollar, then it autocomplete, right? So there are 3 variables, x, y, and the probability. So we want x equal to 2. X double equal, because it's a logical condition. It's not equal is to assign the value from the right-hand side to the left-hand side variable, but double equal is a conditional check. So 2. Then after that, the trick is you add a comma. Comma means to the left side of the comma in the square bracket, it is a condition. So I want all the rows in the data set which meet the condition. Then after they are meeting the condition, okay, tell me what are the columns that you want. So I want all the column names. So just run it. So if you run this command, you are going to see that yeah, x are all equal to 2. Then y is 0, 1, 2, 3, 4, and they are probability, the probability. So I'm going to see x equals to 2 here. Row 11, 12, 13, 14, 15. Yeah, so this is a subset that we have obtained. So then after that, we want the probability, right? So we want to find the probability x equal to, then we need to sum all these probability. But before we sum, we need to add it dollar outside this bracket, not inside, outside this bracket. Then you are seeing that for this small chunk of the subset of this entire data frame or data set, then I have three variable, I want the probability. Okay, so now I run it again. You are seeing that 1, 2, 3, 4, 5 values. So there are a probability. Then after that, what shall we do? We're going to sum it. Okay, so I can do this sum parenthesis, then command B, control B, paste it. Then you run it. So it gave you 0.26. So this is a sum of 4%, 6, 9, 4%, and 3%. Sum them together, you get 26%, 0.26. Another way is to directly obtain the value. Okay, so sum the data set's probability and giving a condition. There's another way to do it. But I'm showing you step by step. It's easier for you to verify whether the result is correct. So easier for you to verify. Then, okay, so we get the first one, right? 0.26. Then probability x less than equal to 2 and at the same time y less or equal to 2. Okay, so this is a probability. Okay. So we want two conditions. Okay, so we can still use this concept, right? We can still use this concept. We want to do the second question. Okay. The probability x equal to 2 and the same time the not equal to 2, less or equal to 2, and y is also less equal to 2, right? Less equal to 2. Then we add a comma there, then everything show me. Okay. So x less or equal to 2, y less or equal to 2, all the combinations where x and y are less than equal to 2. How many? How many individual are there? I'm not sure. I can use length to find length length of this. So I can find no, not 3, sorry. So 3 is telling you how many variables are there. So I need to add the probability here. Oh, dollar, I'm interested in probability. So these are the probabilities. So I'm going to find the length of this probability, then tell me how many are there. It has actually 9. So there's 9 of them. So now we want all the probability which meet this condition, add them together. Add them together. So we are going to have a sum of these 9 probabilities. Sum of these 9 probabilities, 0.69. 0.69. So next is a single line, which will also give you 0.69. So, but basically these are the rows. These are the 9 rows, 9 different combinations of x and y values and their corresponding probability. Sum them together. Then probably x equal to y. Okay, again, now probability x equal to y. So we'll be using this method. Probability x not less or equal to 2. Instead, we type it is equal to another variable one. It's quite flexible, right? So it's quite flexible. So I see 0, 0, 1, 1, 2, 2, 3, 3. We just verify 1. Okay, say x equal to 3, y equal to 3. This is row number 19. So let's go back to Q1. Row number 19, 3, 3, 0.03. It's correct, right? That 13 is 2, 2, 0.09. All correct. So we have 1, 2, 3, 4, 4 lines, and so 4 probabilities. Dollar probability. So these are the 4. Okay, you add them together, it should be equal to 0.31. It should be 0.31 if you add them together. Okay, so this is question 1. Okay, so primarily how to reading a data set, then how to do the subletting to get a portion of those data set rows which meet certain conditions. So there is a logical operator there. and or then double equal, smaller or smaller equal, and so on. So second one is download the data Q5 question 2.csv. Then you will see these are 200 household surveys. You can use view, and survey household are likely to be selected as column the frequency of the observations. Okay, so we're going to read these files first. So now Q2, question 2, read the CSV file, choose header equal to true because our data actually have header. Header row, that means first row in the data set is a header. So X, Y, and frequency will be used as variable name. And there's 28 rows. Frequency, you sum them together is 200. So 200 household is shown here. Okay, let's read. Question 2. Okay, done. So I see 28 observations, 3 variables. So this is Q2, X, Y, and frequency. X, Y, and frequency. Okay. So now let's read this again. Calculate the probability of different values of X and Y. You can do this by based on the frequency column, then sum together to see how many total household are there. Okay. Then we'll calculate a few of the different probabilities. So first, sum the Q2 dollar XY frequency. Okay, so I have a few frequency. So it'll be 28. How do you verify? You use length, 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 verify the frequency. Okay, 28. You can also do this. This also says 28 observations. So you can do STRs. STR means structure. You can do a structure. So it says a data frame, 28 observations of 3 variables. So basically it's the data that is shown here. Structure, STR means structure. Then we're interested in the total frequencies because we are going to convert the frequency to probability, right? Frequency is count of the occurrence divided by the sum of it. Do the sum of it. Okay, so these are the 28 probabilities. These are the 28 probability. These are actually the probability, right? We also want to verify this is the sum of these 28 probability equal to 1. So we want to calculate the sum of all those probabilities should equal to 1. That's what it verifies. Yeah, equal to 1, which is good. Then you can also use the sum of these 200. Then we are going to create a new variable called probability. So we call it Q2 probability. Shall we call it probability? Calculate the probability, then treat this one. Okay. Q2 dollar, you can write there is only X, Y, and the frequency at the moment, right? So Q2 only has 3 variables. So I'm going to create one fourth column. We call it a probability, but probability is okay, pretty long. Okay, so we use this probability, although it's long. So we can type it. It is equivalent to this one. So this is a probability. You can use the sum of the frequency, which is 200 now, or the lower formula. They are the same. They are the same. Okay. So now you look at. Now you are seeing after running this line 68, you are seeing that there's one more variable being created. So you go to Q2, you are seeing this probability assigned for each line. Okay. You can also run the next line, the line 70. Line 70, you use 200 instead of each time you recalculate the frequency, so it's slightly easier. Then run it. Then the new probability will overwrite the original probability because they have the same name. So we verified, you see there's no change. But what if we do this instead of this probability, we type it, say just 200. We just assign to 200. Run it. Assign to 200, then you go to Q2, you see the probability become all 200. So this is showing you that when you have the same variable name, it will be overwritten. Then yeah, we use the correct one. Use the correct probability. Okay, so these are calculated probability. So now we have the probability. Next is we are going to see how to calculate each of these probability joint probability. X equal to 4, y equal to 0. Again, do you remember how shall we do that? Q 2.1, Q 2.1. We want x equal to 4, y equal to 0. So these are Q2 square bracket, comma, to the left of the comma, add the condition. So Q2 dollar x, what is x equal to 4? And at the same time, Q2 dollar y equal to 0. So this is Q2.1. Q2.1. Then let's display all of those. Only one, x equal to 4, y equal to 0, frequency 2, probability 0.01. So the answer is probably 0.01. Okay, easy. Then next is what is the marginal probability x equal to 4? Okay, so copy x equal to 4, 2.2. 2.2 x equal to 4. So just x equal to 4 and show me all the rows that x equal to 4. All the observations x equal to 4. 1, 2, 3, 4. There are 4 instances and their frequency and their probability. So you sum the probability together. Get the probability, dollar probability. Then you have these 4 values and sum them. Additional 2 here. Yeah. Q2. Miss one Q2. Q2. Okay, 0.21. Now it is the same as if you calculate using give me all the probability and the condition of x equal to 4. So they will give you the 2 same value. But I recommend you use this method that I'm showing you here. So it's easier for you to verify. Then 2.3, what is the conditional probability distribution of y given x equal to 4? So basically you want to see x equal to 4, then what is a corresponding y value? It's actually shown here, x equal to 4, what is a y value? It is this one. X equal to 4, y value, you see. So these are the x equal to 4, and y you can take y equal to 0, 1, 2, 3, and what is the joint probability. Then you convert the joint probability to conditional probability by using these joint probability divided by the sum of all these probabilities. Okay, all these probabilities. Then what you can do here is, yeah, there is an orthodox way for you to show it. So x equal to 1 and yeah, the next one is the standard way. Okay, let me see if I am giving you a better, easier ways to do probability. Then you get all this probability. Then you divide by the sum of this probability is 0.21. Actually, you notice the sum of it is 0.21. The sum of them. Okay, sum Q2 probability. The sum is 0.21. Okay, right. Sum is 0.21. Then the 1, 2, 3, 4 probabilities are there. These are the 4 probability, and the sum of the probability is 0.21. So you use this each of the probability divided by 0.21. Then each of these probability divided by 0.21. Then it's easier, just divide it. Okay, so we are going to get 1, 2, 3, 4, 4 probabilities. So 4 probabilities, which is should be equivalent to these 4. So just show it. Just show it. These 4. What is the value of these 4? Yeah. P 0, 4, 1, 4, 3, 4, 2, 4, 3, 4. Yeah, they are the same. Okay, that's it. Then we're ready. So conditional probability distribution we already displayed. This is a conditional probability distribution. 2.4. What is the conditional mean of y given x equal to 4? Okay, what is the conditional mean? What is the expected value of y when x equal to 4? Okay, so we use the y value times its corresponding probability. Okay, so we have these four probability. Y equal to 0, 0.04. Y equal to 1, 0.59, blah, blah. So these are the four values. Okay, for you to calculate easier is 0.4, 1, 2, 3, 4. So these are the four probability, right? So then this one is y equal to 1. So y equal to 0. Then this one is y equal to 1. This one y equal to 2. This one y equal to 3. Okay, right. 1 times 0 is 0. 1 times y equal to 2, y equal to 3. So these are the four values. Okay, so next is we sum them together. Sum them together. Sum them together, SUN. Sum them together. Running. Yeah. 1.4285. So 1.4285. You can use a few other methods to run it. This will give you EX4. X equal to 4. Expected y of x4 is same. You can find from here as well. Or you can use another method, calculate. So in the end, the key thing is expected value of y when x equal to 4 is the weighted sum, okay? Y value equal to 0 times the probability of y equal to 0 when x equal to 4. Then probability of y equal to 1 times the conditional probability of y equal to 1 given x equal to 4. Then sum them together. Then you get 1.428. Question 3. By the way, 5 and 6 are optional. You can attempt. And 7. Suppose that x and y, question 3, x and y are random variables such that variance x equal to 9, variance y equal to 4. And low xy is a linear correlation coefficient of xy is minus 0.515. Use the data to estimate the following. So x plus y, x minus y, the variance of these and variance of that. Okay, 1, 2, 3, 4. So recall this is the thing that we need to use the few formulas shown here. So primarily it's applying the formula here to solve the problem. Okay, so covariance and low linear correlation coefficient, what is their relationship? So covariance is linear correlation coefficient times the standard deviation of x times the standard deviation of x to y. Okay, so if you have that formula ready, then it'll be easier for you. So variance x is what, 9. Okay, let me clear everything. Okay, variance x is 9 for Q3. Variance y is 4. The low xy is minus 0.15. Okay, so next is covariance xy is low xy times sigma x times sigma y. So sigma x, sigma y is the square root of 9 and 4. Okay, so square root of 9 and 4, square root of y is 4. Okay, so then times low. Then what do you have? You run it minus 0.9. Okay, minus 0.9. You can also highlight these. They highlight a part of it, then you run it. They're going to show 3. Then you highlight part of it, you run it, it should get you 2. Yeah, because the square root of 4 is 2. Then the variance of low xy is minus. Then you sum them, these 3 together, it will give you minus 0.9. Okay, So now we have all these formulas. X plus y variance is variance x plus variance y times 2 times covariance of xy. Covariance equal. Yeah, y, covariance xy. Covariance xy minus 0.95. Okay, so you run it. X plus y plus 2 times this. So 11.12 is the question of 3.1 variance x plus y. Then what about variance x minus y? X minus y. So you have minus y here. 2 times a and b. A is 1, b is minus 1. So 1 times minus 1, then times 2. So we actually minus these 2. So 14.8. Yeah, 14.8 is the variance x minus 1. Then the third one is A, B, C. A is 2, B is minus 3, C is 4. A, B, C. A, B, C. A is 1, B is minus 1. A is 2, B is minus 3, C is 4. Okay, so I have 2 times 2 times variance x plus minus 3, which is a b, right? Powered 2, right? Then third one is 2ab, right? 2 times a times b. 2 times a plus b. Then this is the formula. So get 82.8. Then the last one is variance minus x minus y is actually equivalent to variance x plus y. Okay, so get a minus there out, then minus 1 squared, you get 1. So it is the same as 3.1, 11.2, 11.2. So this is testing you the coefficient inside the parentheses. X be a random variable representing the weather of the day. X can be rainy, sunny, and cloudy. Okay, Y is average temperature, degrees Celsius of a day. Z is the amount of iced tea sold at the canteen one in a day. Okay, so look at 4.1. Define the meaning of the conditional probability X can vary. Then, but Y had been fixed. Y equal to 20. Y means 20 degrees Celsius. How is it different from px? Okay, what is the conditional distribution of px given y equal to 20? Okay, so y equal to 20 is meaning that the condition is from today and in the future, every day is 20 degrees Celsius. I treat it in this way. That's fixed. So for a 20 degrees Celsius, what's the likelihood for? Meaning a rainy day, sunny day, and cloudy. 20 degrees Celsius. Most likely, sunny and cloudy may be higher probability, then raining will be lower. Let's say raining is 0.1, then we remaining have 0.9, right? 0.9. Then we say sunny is 0.25, then cloudy is 0.25. So 0.25 plus 0.25, then plus 0.1, you get 100%. So that's the conditional probability here because X can only take 3 values. Raining, sunny, cloudy. How is it different from PX? PX is, yeah, then consider all the variable temperature in the past instead of only picking up those days when the temperature y equal to 20. So we consider more days in the past than what is the marginal probability for getting raining, sunny, and cloudy. But I think Singapore, the raining maybe go higher. Then sunny and cloudy will slightly drop. So what does EY x equal to sunny mean? Okay, so what is the temperature when we know, given that it is a sunny day in here? It is sunny day, what is the temperature? It is a sunny day, generally the temperature will be pretty high, right? Maybe 33 degrees Celsius, 35 degrees Celsius, that's more likely. Okay, so it means what is the average temperature? Obviously, here is the expected value. So what is the average temperature when the weather outlook is sunny? Then we look at all the past days, past 10 years, filter out all those sunny days. and calculate the average temperature. Yeah, so that is the expected temperature or average temperature when it's a sunny day. Question 4, common sense to okay. Huh? Oh, they're here. Question 4, yeah. Probability distribution of rainy, sunny, cloudy when the temperature is 20 degrees fixed. So the average temperature of a sunny day is expected value of temperature y given x is sunny. So easy, y equal to 35 degrees. Oh, here is defining ice cream. Common sense to compare y equal to 35 degrees Celsius a day, very hot. Expected Z. Expected Z is the number of iced tea being sold. So average iced tea to be sold on a hot day, 35 degrees. And easy is expected daily iced tea to be sold, no matter it is a hot day or cool day. Okay, so hot day, we expect it to be, we want more iced beverage, then it's likely to be sold more. So easy given y equal to a high temperature is, by common sense, more sales than a when we consider all the days. Okay, so that's the one. So and I added one. If today is a minus 20 degrees in the in the cold region, what is their relationship? So in general, our assumption is the hotter the day, the warmer the day, the more iced tea, iced beverage will be sold. The cooler the day, it'll be lesser to be sold. So the relationship by common sense is this. Okay, question 5. Before 1950, most medical scientists believed that lung cancer be caused by air pollution, coal burning, blah, blah, blah. Then we're thinking that at the time smoking may play a role. So below is a data table. Okay, so these are two random variables, two variables, lung cancer, number of lung cancer, and number of smokers. Smoker, yes or no, then lung cancer, yes or no. So this is a table. So present your answer to 1 to 5 based on the below. What is the marginal probability of x? Probability of x equal to 1 and probability x equal to 0, 2, 3, 4. Okay, so we are going to look at this. So when you are having this kind of table, so it's better for you to draw a like a pie chart. Pie chart. So I've drawn a pie chart for you. So here, so this is the case. So cancer 1, no cancer 0, smoker y equal to 1, then non-smoker y equal to 0. Or you can draw a pie chart. So when x equal to 1, smoker and cancer and smoker, you have 6, 8, 8. So no cancer, x equal to 0, y equal to 1, you have 6, 5, 0. So in total, these are larger portion versus those ones who are getting cancer. Those are non-smokers. Non-smokers y equal to 0, and cancer 21. Then no smoker and no cancer is 59. 59. So we are going to see this table. Okay, so once you have this table, that'll be much easier for you. Okay, so next is we look at this. Give me one moment. Okay. You're asking for x equal to 1. So smoker. What is the marginal probability of smoker and a non-smoker? So how do you calculate this one? Smoker. How many smokers are there? What is the marginal probability? X, then x equal to 1. Okay, x equal to 1. Also, this is lung cancer. Okay, lung cancer, you have 709. Okay, 709. 709 versus entire population, 709 times 2, so I get 0.5. Question 1, you get 0.5. 0.5. Okay, so 0.5. Then what is the marginal probability y equal to 1 and y equal to 0? y equal to 1 is 688 plus 650 divided by this double of 209. So that's the proportion of smokers in this data set. It's not necessary to be in the natural population, but in this particular data set, it shows 94% of the subject, the people get surveyed are smokers. So it's actually very high. So we treat this data as the universe that we are working on, okay? Then the probability of y equal to 0. So it is not a smoker, is 21 plus 59 divided by 1418. 1418. Then it is about 5%, 1 minus 95%. So 5.3. 5.3 is, this is a bar. When you see a bar, it is conditional probability, right? Conditional probability. Y equal to 1. Y equal to 1. So these are already lung cancer. So the no lung cancer, you just completely ignore. So your entire universe is now y equal to 1. Oh, sorry. Y equal to 1 is all the smokers, okay? So out of these smokers, how many of them are getting cancer? Okay, 688 divided by 688 plus 650. So because they are all y equal to 1. Lung cancer, and they are smoker. How many smokers are there? These are the number of smokers, y equal to 1. Then out of these smokers, out of them, how many are getting lung cancer? So 688, okay. So 688 divided by this is about 51%. So then the next one is y equal to 0. So non-smoker. So in the non-smokers, how many are getting lung cancer? So 21 out of 21 plus 59. 21. So these are about 26% of the non-smoker are getting cancer. Then question 4. Do X and Y appear independent to each other? How do you measure it's independent or not independent? You need to calculate these, right? So independent or independent? X and Y. So Px equal to 1. What is the probability? Lung cancer. Let's say calculate lung cancer. Then is 0.5. Now we already know it. Then we want to calculate whether PA equal to PA given B, right? So if they are equal, then it's independent. If they are not equal, then they are not independent. So the marginal probability is 0.5 of getting a cancer. So we want to find out whether when knowing that that person is a smoker or non-smoker, it will change the probability. If it doesn't change, that means whether we know that person is smoker and not smoker, it doesn't affect the lung cancer probability. Then we say that smoking and the lung cancer are independent. So now we try to calculate, yes, lung cancer and Y equal to smoker. So yes, lung cancer and 1 equal to smoker. So actually we calculate earlier. Lung cancer and smoker, right? So smoker is here, lung cancer is here. So 688 divided by 688 plus 650. This one, it gives you 0.5142. So these two values, you compare whether it's same or not same. So obviously they are not same, so they are not independent. Not independent. You can also verify using another way. So x equal to 0. Then given x and y, x equal to 0 given y equal to smoker. So compare these two, they are also not equal. So they are not equal. So they are not independent. Not independent. P A given B, is it equal to P A? Is it equal? Or you can say P B given A is equal to PB. If these two are all equal, then we say A and B, these two random variables, are independent. Okay, 5, Q5. Why did the scientists not just looking at the column of X and Y to make a decision? Okay, so yeah, let's have a look. The question and the tutorial solutions, week 5. Fine. Okay, so 5.5. Number of smokers and the percentage of non-smokers. They will need to also check whether it is true for these before they can conclude the variables are independent or not independent. Yeah. Okay. So I have a small variations for you. That is, we are going to change a few numbers. So these are bonus. So assuming a new survey result, so change the probability of y equal to 1 smoker of not getting lung cancer from 650 to 1932. Then 1932. Okay, so basically we want to change this one from 650 to 1932. Then the total no cancer change from 709 to 1991. So 1991 is 1932 plus 159. You get 1991. So this is the additional settings for you. So you can do a calculation to find out whether smoking and getting lung cancer is independent or not independent. You can try from here. Recalculate the probability of getting lung cancer now changed. 709 divided by 709 plus 1991 is about 26%. Total of getting not getting the cancer, not getting the cancer. This one, yes, lung cancer. Okay, 709 divided by 709 plus 1991. So these are the marginal probability of getting cancer, about 26%. About 26%. Then next is we want to calculate, yes, lung cancer and smoker. So how many smoker do we have here? I have smoker here. 688 plus 1932. Okay, so there are so many smokers. Then out of them, how many are getting lung cancer? This is a value 688 divided by. Then you are seeing these two are very close. Above two are now equal. I will calculate now equal. Then we can now calculate the no lung cancer. No, not a lung cancer. Is one, not lung cancer, is 1991 divided by 709 plus 1991. No, not lung cancer. It's actually 1 minus getting the cancer. 1 minus getting the cancer is about 73% not getting the lung cancer. So now we check not getting lung cancer, you are a smoker, what is the probability? They are also the same. So I'm saying, okay, it is equivalent to getting a above two are now equal. So we're saying that A and B can be considered as independent. Okay. This also mentions why we need to look at the four numbers, not only the smoker, but the non-smoker as well. Okay, so that's all for our week 5. Okay, thank you everyone. Bye bye.